Okay, now I want to plot multiple vectors and at irregular places on the graph. To make my graph look better, I want to make it larger by supplying a figure size parameter here, figure size. So let's make this 9 by 9. Run the program to see the frame. Okay, this looks good. First, I want to supply x coordinates of my vectors. So x coordinates, I can, for example, give -2, 0, and 3. And for y coordinates, let's put them at the center. And this one on -1, for example. So I am giving the coordinates here. Next, the vectors. Let's make the vector components ux. Okay, ux. Let's make these vectors the same at the beginning. Okay, so these are a unit vector in the x direction, all three. So I have 3 coordinates and 3 vectors to be placed on the frame on the right. So before putting the vectors, let me show you the coordinates that I will be putting the vectors on. So x coordinate and y coordinates. I want to show them with a O figure. So okay, at these 3 points, as I defined here, I want to put my vectors. I use Kubert-Plot. First, I tell which coordinates I want my vectors, and then give the components of the vectors, x and y components. Next, I do the scaling and units. This is regular things we've done before. So let me run this now. For example, make this vector a unit. This is not a unit vector, but now 45 degrees. Okay, and how about we make this a vector in the negative x direction? Okay, good. Now basically, I can now put vectors anywhere I want. Okay, let's do something interesting now. I want to use x coordinates as a NumPy array. Let's say linspace from -3 to 3 and 7 points there. And for my y coordinates, I want to make NumPy zeros. Okay, so 7 zeros. Then I need 7 vectors here. So NumPy, and then how about we do random vectors, 7 random vectors by the random command. So basically I am supplying a NumPy list for x coordinates and another NumPy array for y coordinates, and these are the vectors. So let's see what this looks like. Okay, the y coordinates are the same and the vectors are random vectors. Lastly, I can also do a linspace here as well. So let's see. Okay, so y is a linspace, x is a linspace, and then we have random vectors. Also, why not? I want to show you complete random vectors. So the locations will be random now. And then generalize it with an n. Okay, so I have random coordinates and random vectors. And how many of them? Let's have 10 of them. So 10 random vectors at different places. Okay. Now I want to show you how to put vectors at regular points on a grid. I will be using the same frame. Let's clear the screen. To create a regular grid and to obtain the coordinates of that grid, we use the following commands. First, I want an x numpy linspace, for example, from -4 to 4. Let's have 9 points, including the 0. And then let's do the same for y. So if I run this to look, x is numbers from -4 to 4, in total 9 numbers, and the y is similar. To create a grid, we use a command, a function, a numpy function called mesh grid, and input this x and y into the mesh grid function. So I am inputting an x for the x dimension and the y array for the y dimension. And this returns a grid. The grid has x and y coordinates. So to make them different, I assign them to x and y, capital X and y. So if when you run this one, let me show you x and y. Once I have a regular grid of x coordinates and y coordinates, I can put vectors on these coordinates. But before that, let me show you the grid. I want to turn this off and want to plot the grid. So this is the x coordinates of the grid and that's the y coordinate of the grid. Let me run this. So I have this regular grid now, x coordinates and y coordinates. I want to put a vector. I can put a different vector on each one of this. But before that, let's put the same vector on each of these points. This is a 9 by 9 grid, so I can have once 9 by 9. You need another parenthesis like this. Let's have a look if this, yes, so one 9 by 9. And for the y coordinate, I can, how about we have zeros, 9 by 9. So can you guess what kind of a figure we will get once we draw the curve plot here? So my x coordinates this time are capital X and capital Y, and these are my vector components, x components and the y components. So I didn't run this one, so let me run it. So the x components and the y components. I want to plot the coordinates and then plot vectors at these coordinates. Let's see the result. So I have a vector at each of these points, and they are, of course, the same vector. Now, instead of putting this 9 here, you can also say I want ones like the shape of X and zeros like the shape of Y or X, since they are the same shape. So let me put an X there. Look, gives you the same one. Let's see what this looks like. Ones like so. Let's make this half in the Y direction. So those are my vectors. Okay, and to see that you can actually assign different vectors, I want to also do a random. This time you have to supply the shape directly 9 by 9. Some of these vectors might be large, so let's divide them by 3 to have nice small vectors. Okay, so random vectors at regular points. Okay, I still have my coordinates, so I can turn them off if I want to take them off. And now I don't have the coordinate points. Okay. I want to show you that you can define your vectors as functions of the coordinate, So my vector components can be, for example, x plus y, and y components x minus y. To show you how this works, let me run this part. So these are my coordinates. X plus y is element-wise sum of these two. So here is another array that has the same shape and size of the coordinate axes, x and y. So x minus y would look similar. So how about I use as the components of the vector x plus y, x minus y. Let's see what this looks like. Okay, run. Good. So I have, it looks like I have different arrows all over. Let's increase the scale. Increasing this parameter here makes your arrows larger, smaller, so we can see the pattern better. Okay, I have variable vectors at xy coordinates now. I can increase the resolution by spacing my x and y variables with higher numbers. So this time I have 20 by 20 arrays of x and y, and the mesh grid will be accordingly 400 element mesh grid, and the components will be 400 elements each. If you run it this way, you will see the arrows at each point. This clearly demonstrates a kind of a flow. Let's try another scale. Okay. This is also much helpful. Now let's do something more fancy now. How about I define an R vector that is the distance from the origin. If these are the coordinates, then this is the distance from the origin. So I can now use R, for example, in a sine function and in a cosine function for the y component. This will be another flow. Let's see what it looks like. Since my sine and cosine outputs are between -1 and 1, I can scale it back to 1. Okay. So this is what it looks like. So perhaps making the scale 5 will make the pattern look better. Okay, think about what we have done. We are ready to do something interesting now. So let's create real flows. From aerodynamics, you should remember we have a sink, a source, and vortex flow. So I want to create those kind of flows using my framework. I have my regular grid and I have my distance vector here. So if the components are given in this way, x components are x over r squared, x over r squared, and y components given as r squared. Let's have a look what this flow looks like. Okay, this kind of a flow is a source flow. So it is as if we have a source here and the flow speed ux and uy are the flow speed, which is larger here, and it becomes smaller as it moves away from the origin. Maybe a different scale make the plot better. So let's see. Okay, so this is what is called a source flow. To make it a sink, this is going to reverse the arrows. Look at this. Okay, so as if we have a sink here, the flow comes and is destroyed at this point. Okay, so pay attention here how I do the x flow velocity is x over r squared and y velocity is y over r squared. Okay, perhaps a more interesting one is a vortex flow, which is given as this. So x flow is proportional to y over r squared, and y is proportional to minus x over r squared. Let me first plot this. Okay, now in this case, the vectors, the magnitude of the vectors gets smaller as they move away from the origin, and the vectors swirl around the origin point, and it is not defined at the origin, but around it. Okay. If you wonder what it looks like if I didn't have the negative there, the picture will change completely. So we have flow approaching this point, and then this is a saddle point now. It is then moving away from there. Okay. The point of doing this is now you can play with it using Python, use different functions, etc. I think at this point I can also introduce the stream plot, PLT stream plot with the same parameters. Okay, I want to take away the Cubert plot. Now Matplotlib has a stream plot function as well. I use it with the same coordinates and the vector components, and it gives me a really nice output of the flow. So this is the flow with saddle point over there. Let's make this the vortex flow. Okay, here's the nice vortex flow I can see. So this is clockwise. To make it counterclockwise, of course you multiply it with -1. There you have now the counterclockwise. And let's also look at the sink and the source. This is the source one. So source flow, and then the sink flow would be the negative direction. Okay, so it's really nice. We have a global picture of the arrows. To conclude this video, I want to show you how you can shift the origin of a flow around the frame. So this is how I begin with that. Okay, if I want my flow, for example, this is a sink flow, and I want to move it to x equals to x sink, y sink. Let's move it to a point 2.3. So where is that point? X is 2 and y is 3. So I want to move this origin here. Basically, I update this. I think the best way is to create a new coordinate axis. X underscore is x minus x underscore sink, and the same for y. So these lines shift the vectors, the flow origins to 2.2 and 3. So this is going to be my R. I want to use now the shifted coordinates. Here is the shifted X, the shifted Y. Okay, so I will be plotting now. Of course. Okay, I will be plotting at the same point, but with different components of the vectors. So have a look at this. So my flow is moved to this side. I can change the location. For example, let's move it to -3, -3. Okay, now the flow is here. Let's change this to a vortex flow at the same point. One of them must be positive in that case. Okay, so here is a vortex flow at that point. Something additional we can do at this point is how can we superpose two flows on top of one another. Next, I want to show you how to do that. Now I want to show you how to do more than one flow at on the same frame. In other words, I want to superpose more than one flow on top of one another. So clear the console. So I will have one flow and then another one after that. So I can simply copy this here. So one flow is at that point and it's a vortex flow. And then let's have another flow. This time let's make it at that point. Okay, so this shifts the new coordinates, calculates the R again, and this is going to be my second flow. And this time I will make it so these two, they are both vortex flows, but one is clockwise, the other is counterclockwise. I want to visualize this one by one and then put them together, put them on top of one another. So this is my first flow, clockwise at location -3, 3. And the second flow is there, this time counterclockwise and located at 1, 0. To put them on the same graph, I can do ux is ux1 plus ux2, and then uy is uy1 plus uy2. And then I plot them. I plot the sum of the flow vectors. I do a component-wise sum. So, okay, this is my clockwise, and this is counterclockwise flows. They are same intensity. I can change the intensity of the flows by, for example, increasing the intensity here. Intensity. Let's make this flow twice as powerful as the other one. So just multiply by 2 here and 2 there. So this gives the strength of the flow. I am making it twice in proportion to the other one. See how the flow graph changes after that. Now I made the 1, 0 one more powerful. So you see that this is now less prominent with respect to that one. So in that case, I think it's a good idea to put the strength or the magnitude here, and let's make it 5 and put this as a magnitude there. I am making this one really powerful, 5 times more powerful than the other one. So this dominates the other flow. Let's move this closer to the, so I want to make it close to show you how the flow. So we have a small disturbance, but overall very near this point we have a disturbance to the flow, but otherwise the flow is more regular around. Of course, this is going to, if you make the strength less, we will be able to see the effect of the second vortex more clearly. So this is how you do the superpositions. Let's finish this part by making a sink and a source flow near one another. So I want to put a source flow at -1, and this one will be at +1, 0. And this is the magnitude of my, and I want to make the magnitude 1 again. So to make it a source, remember I use a x here and the y there. And the other one also x for the x component and y for the y component. To make this one a sink, I put negative to each one, and then to make a source, I put positive to that one. So let's see if this works. Okay, yes, I have a, so there is a source here from this point a flow originates, and at that point the flow terminates. So the lines terminate there. I can make them apart. So that is make 2 and 2. So here is the source and there is the sink. We know a spatial flow called a doublet. A doublet is when you have a source and a sink and they are very close to one another. So I leave this as an exercise to you to see how what kind of a flow field you get when you really move a sink and the source close as close as possible. Explore that on your own time. Also, how about we do the sink? This is the sink twice as powerful. It will remove the symmetry from this flow. I also want you to think about a vortex flow and a source flow, for example. Please try different combinations of the flows to learn more about this. These are all very good. How about we have more than 2, 3, 5, 10 or more vortex flows that we want to work with? Of course, in that case, you need a for loop. I want to show you how to superpose a number of vortex flows using an iteration, using a for iteration next. So at that point, I want to define my vortex x coordinates, vortex y coordinates, and vortex intensities. Let's say, for example, vortex y coordinates at 3, 1, and about 3, and x coordinates. I actually want this to be my x coordinates, and y coordinates can be 0, 0, and 2. So I have 3 vortices, their x coordinates, y coordinates, and then vortex intensity here. Inside the for loop, I want to go over each vortex and add it to a flow field. So for I want to go through these lists, but I want to zip them together at first. For I, j, k, I will be for the x coordinate of the vortex, j for the y coordinate, k for the intensity of the vortex. So zip vortex x, vortex y, vortex e, I. Okay. So I can take that away. My x underscore and y underscore will be x minus I. Remember, I here is the x coordinates. In turn, for each iteration, it will take one x coordinate from the list. So j holds the y coordinate, and then intensity is in the k coordinate. So I can do the radius. First component of my velocity field. To make this a vortex, remember this is x and that is y, and then I can make a minus here to make it a vortex. Okay, only need the k here. I must multiply it by k to give it the strength. So this is the flow field due to one of the vortices. So I want to add this to my field ux plus 1, or better I can write it u. It will be more intuitive if we do it this way. So velocity field is equal to the velocity field plus the new field due to the new vortex. I need to define this on top there. So I add the flow field due to each vortex to a global field here. So my global field should be zeros like x and zeros like y. Okay, so the warnings go away now. And then I must plot. I want to plot Vx and Vy. Okay, before running, let's look at what we have done. After creating the grid, I define my vortices by their xy coordinate and their intensities, then create a uniform field of no flow, zero flow field to begin with, and then in turn I add each vertex flow calculated here to my velocity field, and then plot the final velocity field. So let's see. Okay, here is my three vortices at different coordinates. So they are all in the clockwise direction, and this one at point 32 is the greatest one. This is the largest one. So actually this is twice more powerful. So make it even more, 5. It almost eat this vortex up, but we can still see the other one there. How about I to make it a negative one? Okay. The good thing about this notation is now I can add more vortices and more. I can add any number of vortexes I want, and the iteration will take care of that. So I want to put a vortex over there. How can I do that? The x coordinate is -4, and the y coordinate is 4. And then the intensity can be, for example, 2. So, and then run. The warnings, don't worry about the warnings much. So this is really at the 4 over there, so I can't see it. It will be better if I increase my frame a little more so that I can see the vortex created there. So this time I have 4 vortices. So stream plot makes it look much better, but why not have a look at with the Cuvert plots? Scale, let's do this 5 for now, and then see how it works. Okay. Of course, there are some irregularities as you come close to the origin, but you should appreciate now more the stream plot because it takes care of much of those irregularities, singularities by itself and gives you a nice smooth flow field. I suggest you to go to Python documentation and look for extra parameters for the stream plot function. You might find those helpful too. Okay, this concludes our flow field visualizations. We will be using this around an airframe in the coming videos.